Hello everybody, I want to thank you for watching this video. We're going to quickly get through Chapter 10, Correlation and Regression, and then we'll be done with the Introduction to Statistics. I hope you've enjoyed the class. I've really enjoyed teaching it, and let's get started. And I want to thank you all for working so hard in the class. I really appreciate it. We're only going to be touching the surface of correlation and regression. This is a very big topic in statistics, and let's dive right in. So, as I mentioned in class, correlation and regression is about trying to find a connection between two variables. It's trying to understand, is variable X causing or influencing variable Y somehow? And correlation is just about looking at that connection. Regression, on the other hand, is actually about finding a line of best fit or finding a line that goes through our data so that we can make predictions about the future. And so that's the idea between correlation and regression. Similar ideas, and a really interesting part of statistics. So when we say correlation, as I mentioned, we're looking to see if two variables seem to move together. We say that there's a positive correlation or a direct correlation if the variables move together. So if one goes up, the other goes up. If one goes down, the other goes down. That would be a positive correlation. On the other hand, we could have a negative correlation, which means if one variable goes up, the other one goes down, or vice versa. If the first one goes up, the second one goes down. That would be a negative correlation or an indirect correlation. And so we use the variable R, the correlation coefficient R, to measure the strength of the correlation. And let's take a look at that. There we go. So the correlation variable R is a value between -1 and 1. And so a correlation of 1 is a perfect positive correlation between the two variables, meaning the two variables go together. A correlation of 0 means that the two variables don't go with each other at all. And a correlation of -1 means that the variables move in opposite directions of each other. And so interestingly, R is not affected by the choice of X or Y, so you can flip the two variables and R will be the same. And R, you can think of it as measuring the strength of the relationship between the two variables. And as we'll see in a minute, and this whole process is very much affected by outliers. Now, it's really important to understand, and I've said it before, that correlation does not imply causation. These statistics tests are kind of like a flashlight. They'll show you what is happening, if you've done it correctly. However, they won't show you why it is happening. It might be the case that the first variable is causing the second, but maybe the second one is causing the first. So the direction of the causation can be a question. In addition, there might be some third variable that you didn't include in your study that actually causes both of them to happen. And so they look like they're moving together, but really there's a third variable that's in charge. And before we even do a correlation, it's a good idea to look at a scatter plot to see if it even makes sense to do the correlation, because if they don't appear to be linearly moving together, there's really no point to even doing the correlation. So let's keep going. It's important that our data come from a simple random sample, as we've talked about before. That's much easier said than done, as I've tried to explain. It's very difficult to get random samples. As we'll see, outliers really mess this up, and so you need to remove them if you feel comfortable doing that. And you should always look visually to see if there's a straight line pattern in your data. There might be a curved pattern in your data, in which case a different kind of curve could be used. You don't have to use a line to do a regression. You can use a curved line. We're only going to be using straight lines, but you can use curved lines or even a thing called a rolling average that moves along as the data moves up and down. You see those in the stock market a lot with people looking at stocks moving around. The price of stocks, I should say. We also have the variable R squared, which is indeed just R squared. R squared goes between 0 and 1, and you can kind of think of it as telling you how much of the data can be explained by the variable. As I mentioned, R goes between -1 and 1, but you'll almost never see a correlation of -1 or 1 or 0. I mean, in fact, if that has happened, probably somebody's rigged it somehow, because that's just so unusual. Statistics is too messy for that. Usually you'll get some kind of weird decimal, and that explains the connection. And so the R squared sort of tells you how much of the data is explained. And so let's actually just take a look at an example really fast. So imagine we have the following. Here we have a scatter plot. And you can see that this data is pretty tight. You can see it's forming a linear pattern. And now imagine, now imagine we have a scatter plot. And the data looks more like this. Okay, well, what the computer will do, as we'll see, is the computer will try to draw the best line it can through the data, okay? And so you get the same regression line, you get the same line through the data, but you're going to get a very different R squared. So the R squared of this data would probably be something like 0.95, meaning that it appears that 95% of the movement of X is causing the movement of Y. And so you can use this to make predictions. So if I give you an X, if I give you a special X value, you can use that to make a prediction of what you think the Y value will be for that X. However, the R squared over here is probably a lot lower. So the R squared over here is probably something like 0.13, which means that only 13% of the variance over here can actually be explained by this line. And so it's not a very good line. And a lot of times in statistics, we get low R squareds because statistics is complicated. Sometimes, most of the time, there's more than one variable that affects something. And other times, which is really tricky, is something might only happen if certain variables are present. And if one of them is missing, the effect doesn't happen. So you can imagine this gets quite complicated quickly. R squared is not the only statistic that we will use to measure how good this process is. We will also use p-values and alpha as well. Now, I want to show you why outliers can be so bad. So here is some data that has no correlation at all, and so the computer is going to have a really hard time drawing a line through this. And when it does, it's going to give us an R squared probably close to 0, because you can see that the data is just really messy, right? There doesn't seem to be a connection between X and Y. Every value of X seems to have the entire gauntlet of Y values, okay? So it's not a very good use for predicting things. Then imagine I add one point way up here, okay? Way above the other data. What the computer will do is see that point, and because of the way the math works that builds this line, it will make a beeline, it'll make a beeline straight for that outlier and go straight through it. That's fine, but the problem is that because of the way the math works on this, because that point is so much further away than the other ones, the math thinks that this point's bigger and more important, and so this can give you a really high R squared. So you might get an R squared of like, 90, and the reason is because you introduced this one outlier. Even though none of the other points are represented by the line really, or very few, you'll still get a high R squared because of the impact that that outlier has on the data. To the point that if you remove that one point, all of a sudden your R squared goes right back down to close to 0. So that's why we have to be really careful with outliers when we're doing this process. Here's the test statistic that we use. You can see that it comes from n, the number of values, as well as the r and the r squared. And again, r squared is literally just the square of r. We're not going to be using this formula. We'll be using the computer to help us, but we can use this test statistic to get a p-value, which we will then compare to alpha to see if we can use our regression or not. So here's the line for regressions. You might be familiar with this, y equals mx plus b. M is the slope of the line and b is the intercept. Most of the time, b is interesting because b tells us how much the values have in common. So how much all of the variables have in common. That's what b tells you. We're not really interested in that though, because what we're interested in is how one variable is affecting the other. And the variable that represents that is the slope right here, m. And so m is the variable we're really going to be focusing on. That's telling you the impact that one variable is having on the other. In fact, most of this will be ignoring b entirely, and that's okay. Here's what it looks like in statistics. Typically, this is like your parameter equation right here. So y equals alpha plus beta x, or sometimes we use capital B0. And this is kind of your parametric equation, the mysterious parameter that we're trying to estimate. There's some magic line of regression in the population, and we're going to try to estimate it with a sample. And so our sample equation is y hat equals little b0, that's the intercept, plus b1x. And so b1 is the variable we care about, and that's what we'll be studying. And so the parameter equation is capital B naught plus b naught 1. It's interesting to note that you can actually have multiple variables here. You don't just have to have one. And that's where regression gets really interesting, because not only could you have multiple variables, when you do the test, this is called a multivariate regression. When you do the test treats all of the variables as independent of each other. And that's incredibly powerful because you can see how much each variable contributes to the outcome. To give you an example, imagine if we were looking at how much money people had and we're trying to figure out what variables predict how much money people will have. And you could do a whole wide range of variables. You could do personality styles, age, levels of education, where they live, what jobs do they have, how populated is the area where they live, a ton of different variables. And when you do the test, the regression will grab the data of how much money people make and look for how much each variable contributes across your entire population. And that's where this test can get really powerful and also quite complicated. And you have to be very careful to do it correctly. When we're doing a regression, you need to have paired data, meaning for every person, you have a value for all of their variables. That way you can do the analysis. As I've mentioned before, you need to look at the scatter plot to make sure that there is a linear relationship, because again, there might be a curved relationship or no relationship. And you should also look for outliers, which you should throw out if they exist, you need to be careful doing that and disclose that you did that, because that can impact your data. One nice thing about this is that our data doesn't have to come from a normal distribution necessarily, and so that's really helpful as well. Now, we'll talk about this in a moment, but you can only use the equation if the relationship is strong, okay? And so let me show you an example of that. Here, and we're going to see this on the homework. So let's say that we have some data that has a really high R-squared, and that means that we have a really low p-value. So we reject the null hypothesis, by the way, is that there is no relationship, and the alternate hypothesis is that there is a relationship. So if we have a really low value, then that means a really low p-value, then that means we've rejected the null hypothesis, and there does appear to be a relationship between the variable x and the variable y, whatever they are. Now, so if your p-value, if your p-value is less than alpha, meaning there is a relationship between the two variables, then that means you can use the equation to make predictions. So if I give you this x right here, you are allowed to use the equation to say, I predict that this value is going to give us that x value I predict is going to give us this y value, okay? And you can use that. However, let's say that there is not a very strong relationship between the data. And so in other words, let's imagine that we have the following. We have a whole bunch of data that's all over the place. Oops, let me make that a little cleaner. We have data that's all over the place, and some trend line trying to go through our data. And so as a result, this time the p-value is greater than alpha, and that's because the correlation is not very strong. So here the p-value is larger than alpha. If this is the case, and again, we're going to see this in the homework, we can't use the equation. Like, the equation is too bad at making predictions. We can't use it. And so what do? Well, the best we can do in that case, again, we have our two variables, x and y. Every single one of these points is going to have a y value. And so I'm just marking them over here. Every single one of our points will have a y value. And what we can do is we can take the average of all of those y values, and that'll give us maybe something in the middle, which we'll call y bar. So y bar is the average of all the y values. There's also x bar, which would be the average of all the x values. but we're just going to look at y for now. If we cannot use our equation, then y bar is our best guess at what the answer is going to be. And that's really weak. That's really weak. So if we don't have a very good correlation and I say, can you give me a prediction for this value? For that x value, can you give me a prediction? The answer is not really. This line doesn't work because our p-value is greater than alpha. Best I can give you is y bar. That's the best I can give you because that value is in the middle of all the y's. And so maybe, and this may or may not even form a normal distribution, so it's hard to say what's going to happen. And so whether I give you a high x value to predict or a low x value to predict, the prediction we get from all of these values has to be y bar because we failed to reject the null hypothesis. We can't tell if there's a connection between these two variables. Another thing I'd like to show you is when you are making a prediction, you can only make a prediction within the scope of your data. So let's imagine you analyze a bunch of businesses and you notice a connection between how many employees the business has and how much debt the business has. Okay, so down here you have how many employees the business has, and up here you have how much debts the business has. And you find a correlation. Let's imagine there's a correlation because if a company is growing and it's borrowed a bunch of money, maybe they just hired a bunch of people. So that's interesting. But now let's say that you know that your competitor has this many employees right here. Your competitor has that many employees. Well, it's not quite, we can't quite then say, well, according to my equation, that means they're going to have this much debt, which means that they're about to go bankrupt and I'm going to be able to get all of their customers. The reason we can't use the equation for this dot is because the correlation only existed for this data here. The regression equation is great for making predictions within this scope, but as soon as you start going outside of that scope, it's not going to be very reliable at best. It might be as good as guessing. So when you're making a correlation, when you're making predictions, you can only make them within the scope of where your data was that built the regression equation. You should be very careful or not go outside of it. One thing I'd also like to mention is to remember that this is complicated. Many variables only partially contribute to things. The universe is a very gray universe, and so things are complicated, and variables might only be making smaller contributions, not 100%. So as I said, you don't want to go beyond the scope of your data when making predictions. Now you might be wondering, how do we come up with these equations? How do we actually get the line? And there's actually some really cool math behind it. So imagine we have the following. There's our data, and we have two possible regression lines, okay? So here we have regression line A, and here we have regression line B. So A, I think you can tell, is a better line for trying to plot this data. And the reason is but why is A greater than B? I mean, we can see that it's going through more of the points, but what's exactly happening? Well, what the computer is doing is it's measuring the vertical distance between every single dot and the line, and then squaring all those distances and then adding it up, okay? And it would do the same thing for the B line. It would measure all of the points to the B line, either up or down, and measure all of those distances and then square it. And you can see that the B line is going to have more distance than the A line after you've squared them all. That's why A is a better line than B. And what the computer is able to do is look at every single possible line through the data and pick exactly A as the answer of that's the best line. And it uses some wonderful calculus to do it. It's quite complex. It's actually some of the hardest math I had to do, but it's really interesting and really fun. So that's what that least squared property is. It's the least amount of squared error. Those are called residuals. The least amount of distance squared distance from each point to the line. So just to reiterate, if the p-value is larger than alpha, we should not use the equation, and we have to use the mean of the predictions or estimates, which is called y bar. And we'll use StatCrunch to do that. So let's do 2 examples and then we'll look at StatCrunch. So here we have example 1, the regression equation y equals negative 13.6 plus 2.72x has a p-value of 0.311. Find an estimate for the x value 35.5. Assume that alpha was equal to 0.05. Okay, well, we have to be careful here because I know when students sometimes see equations, they just want to jump right into the equation. Oh, x is 35.5, let's just plug it in. Can't quite do that here because look at our p-value. It's 0.311 and the alpha is only 0.05. So because this p-value is greater than the alpha, we cannot use the equation at all. The equation is off limits and the best guess we can give for any x value is y bar. And so in this case, the y value that they all have in common, and the homework will tell you this, is negative 13.6. Okay, it may or may not always be the intercept, I think. However, now imagine the exact same question again, but a low p-value, a lower p-value than alpha. Well, now we can use the equation. And so all you do is you just take the equation, plug in the x value. Remember the order of operations. And so we multiply first and then add. And so there's your y prediction based off of the x prediction. And that's the end of the slideshow. So let's actually just do a few study plans and then we will be done. So just to get started, while I wait for this to load. So here, this is 10.1. Here they're asking us to find a correlation. Here's our data up here. And they have this table here of critical values. We're going to be able to ignore this because we're just going to use the p-value. So don't worry about that little book. Let's open, they're asking which one of these 4 is the data. And you could make a graph and just graph all of these XY points, but we're going to use StatCrunch to do that for us. So let's open it up. So on StatCrunch, to make a scatter plot, this is actually under Graph. You go to Graph and then Scatter Plot. And a whole bunch of options come up, but the only 2 that we need to worry about are X and Y. Literally just make X, X, and Y, Y. Hopefully you can see that okay. All I did was I just made X, X, and Y, Y, and everything else you can ignore. Or play around with if you want, but I'm just going to ignore it. And then I'm going to click Graph or Compute, and you can see it gives me the scatter plot. And so here we should be very careful using a linear scatter plot because we can see that it appears to have a parabola shape, an upside down parabola, or a curved shape. And so a linear correlation is probably not what's happening here. So if I close StatCrunch, we can see that the answer is C. Oops, I'm sorry, I picked the wrong one. After all that work, I picked the wrong one. Sorry, the answer is B. Okay, so now it asks us to find the linear correlation coefficient. So once again, I'm going to click the tiny button to open our data in StatCrunch. And this time, so we did the scatter plot with graph, but the correlation is actually under stat. So you go to stat, and it's under regression. And so it's going to be stat, regression, and then just simple linear. And that's the only test we're going to do. You'll learn about these other tests in more advanced statistics classes. The polynomial would actually be appropriate here because that's what would give you a curved line. But anyway, the one we're going to do for this class is just simple linear. And once again, you just need to do X for X and Y for Y, and that's it. Everything else you don't need to worry about. If you click Compute, it gives you a bunch of different information. If I zoom in a little bit, here's the equation. And so here is the intercept, and here is the slope. The slope number is the one we really care about. Here you can see R, which is the correlation coefficient. And here you see the R squared, which is 0.667. So the correlation is positive, and so it tends to be that as the points get bigger, they both move. As one gets bigger, the other gets bigger, and certainly we saw that. And so the R squared says that this explains about roughly 66-67% of the data, the line that they drew. And in fact, I think it's possible to look at their line. If I go back to Edit, if we move ahead, you can see there's the line that they tried to do to plot the data. So that's the best line the computer could come up with that exists actually to go through the data. So you can also look at the scatter plot that way. I just clicked the little arrows down here. The variable, as I mentioned, that matters is the slope, and the t-statistic and the p-value that we care about go with the slope. So as I mentioned, the intercept is interesting, but we're going to ignore it. The one that matters is the slope, and so here's the test statistic and the p-value that we care about. So the question asks us for r to 3 decimal places, and so that's going to be 0.817 if we round. So 0.817, type that in, and we get it correct. So is there sufficient evidence to say that there's a linear regression? I mean, a connection. And the answer actually, surprisingly, is yes. There does appear to be evidence that there's a linear correlation, because if I run it again, x for x, y for y, if I run it again, you're going to get the p-value for the slope as being 0.0021. That's less than alpha, especially if alpha is 0.05, which they said right here. And so we actually do have evidence for a linear relation. These points, most of them are close enough that it does appear to be a connection. But we also know that when we look at the data, a better description is a curved relation. And so the answer to this one is there is sufficient evidence to support the claim of a linear relation, and that's because the alpha was smaller, the p-value was smaller than alpha. So this p-value here was smaller than alpha. By the way, they also did a ANOVA, which is nice, but we can ignore that. However, the answer they're looking for in this one is that if you look at the scatter plot, it reveals a distinct pattern that is a non-straight line pattern. So that would be the answer to that part. And I believe this second question goes through the exact same steps. So I'll let you go through that one. Okay, so that's 10-1. Let's keep moving. And let me know if you have any questions, obviously. So I believe these are just some multiple choice questions that I've already answered in the first 20 minutes. So I'll let you work through those on your own pace. I do recommend you answer every single one because they're pretty quick. And please just trust me that you should practice all of them. Now let's do the regression ones. So here we go. Okay, so this is a regression one. I'm trying to make it a little bigger. So here we did ICE-Q scores for 20 random couples, and maybe the question is there a connection between the IQ of couples? So if one member of the relationship has a high IQ, maybe that means the other one has a high IQ. Or maybe it's the reverse. Maybe one has a high IQ and one has a low IQ. Or maybe, who knows, maybe it's mixed all over the place. So that's what the question is asking. Here's our equation, y hat equals negative 6.25 plus 1.06x. So that has a positive correlation. So maybe it appears that as one goes up, the other goes up. But here's what we need to look at. We need to look at the p-value. If we have the p-value being less than alpha, we can use the equation. Otherwise, we cannot. So the p-value is 0, and I don't see an alpha. Oh, no, there it is. Use a significance level of 0.05. So we can use this equation because the p-value is smaller than alpha. And so here's how you do it. I'll just open up Notepad real fast. So we have the equation y equals negative 6.25 plus 1.06x. Okay, and they're saying do a prediction for an IQ value of 92. So what we do is we just put in the number 92 here. So, and we just add this up. So grab your calculator. So it's 1.06 times 92 minus 6.25 because we're adding a negative. And we get an answer of 91.27. And you're done. So there is the predicted value. We need to be careful though, because sometimes the p-value is big. So if I look at the second equation, here we're looking at hands and weights to see if there's a connection between, or heights and weights. Is there a connection between how tall you are and how heavy you are? But according to this data, look at this, they had a p-value of 0.19. And so that's a pretty high p-value. Is it bigger than alpha? Yes, it is. Alpha was just 0.05. And so what that means is we cannot use this equation at all. The equation is, the connection just isn't there. And so as a result, if you ask me to make a prediction for you, the best I can give you is the value that's in the middle of the values, which is the mean, right? Or I guess you could do the median, but most of the statisticians use the mean. And so here you can see that the mean is 81.45. That's the answer to this question. We totally ignore the number 164. It doesn't matter what number they tell us. We're not using the equation. The answer is 81.45 no matter what. So that's why you need to be very careful when you look at the p-value and when you look at the alpha, because either the answer is y bar no matter what, or you can use the equation like I did in the previous example. Okay, we have one more quiz to look at and then we're done. So here we go. The suspense. So here they've given us some data for chest size and weight. So maybe the bigger your chest size, the bigger your weight. I don't know. Is there a connection between these two variables? And again, we're just looking for a connection between the two variables. We don't know if one causes the other or the other one causes the first one. We have a rough idea of how much they move together, but there might even be some third variable that we don't even think about. So we really need to be cautious with how much we use this analysis. So they're asking for the equation. So we're going to open up the data in StatCrunch. And once again, it's stat, regression, simple linear. And then just pick your two variables. I recommend just picking them in the order in the dropdown. So chest size for X, because that's the first one, and weight for Y, because that's the second one. And once again, they put in the names of the variables. So you could probably change it to X and Y if you'd like, but here's the equation right here. So notice that they actually put in the name of the variable for X, and they put in the name of the variable for Y, but this is still the connection. The intercept is negative 190.1667, so everybody starts in the negative, and then as your chest size gets bigger, for every inch your chest size gets bigger, it seems that your weight goes up by 13.5. So that's how you interpret that. So let's put in that equation real fast. So the intercept was negative, it says round to one decimal place, so negative 190.2. And the X value was 13.5. So there's our equation. And it says, what is the best predicted weight of a bear? Oh, I see, they're looking at bears. So they're trying to see if there's a connection for bears. So if a bear has 53 inches chest, what's its weight? Well, can we use the equation? Again, can we use the equation? We need to look at the slope p-value. The p-value is 0.0014. That's lower than our alpha, which was 0.05. And so we can use the equation. So I think you can use the equation that they give you here. I think that's okay. So I'm just going to put in, if I open Notepad again, I'm just going to use the equation that we had, which was y equals negative 190.2 plus 13.5x. I think we can just use this equation. So for bears, we put in the number 53. And we'll just calculate that real fast. So 53 times 13.5 equals, and then minus 190.2. We can use the equation because p-value was less than alpha. 525.3 is the answer, hopefully. Fantastic. So the question now is, so if a bear had a chest size of 53 inches, we would predict its weight to be 525. So if the actual bear weighed 475, is that close? That's a really confusing question because I don't know how they define close. I would say that that's not very close because you're off by 80 pounds or you're off by 50 pounds. So I would say that that's not very close, but this is kind of a guess. I'm not sure how they define it. But if it's 50 pounds off, that's about a 10% error because 50 divided by 500 is 10%. So I'm going to put not very close, and hopefully that's right. Okay, I got it right. I wouldn't say it's close. I would not say it's exactly the same. I would not say it's very close. So that was a little bit of a guess, but to me, 50 pounds off is not very, very close. We'll do one more question and then wrap up this video. Okay, so here we have movie budgets. This is a big thing in Hollywood. How much money are you going to make from your movie? Is there a connection between how much a movie makes and how much it costs to make the movie? And so let's run the regression. Let's find our equation. Open up our data. Stats, regression, simple linear. X is the budget, Y is the gross. We're trying to see, does the budget predict what the gross is going to be? Does how much money they spent making the movie predict how much it's going to make? And let's just look at our p-value, just because I'm curious. Wow, that's a good p-value, 0.0003. So, sorry, I'm just looking at some of these other numbers. So R squared is 0.65, so it does a 65% job of explaining the data. So that's kind of interesting. That's not the exact definition of R squared, but it's close enough that we can sort of use that definition. So here's the equation. 18.9 was the intercept. So all the budgets had some profit in common. And then the slope variable was 1.3. So it said round to one decimal place, so 1.3. So in other words, for every dollar of budget, the profit appeared to go up by $1.3. So that's pretty good. I don't think that's how it works in reality, but that's kind of good. So can we use our prediction for $110 million? The answer is yes, because as I mentioned, our p-value was less than alpha. 0.0003 is less than 0.05. So we can use the equation. So this calculation is going to be 110 million times 1.3 plus 18.9. So we would expect that that movie would make $161.9 million. And that's it. So I don't think any of these problems have an alpha greater than 0.5. If they did, I think the answer would just be the intercept. Let's just check these last few to see if that ever happens. Nope, that's a small alpha. Let's check question 3. Stats, regression, simple linear, x, x, y, y. That is a 0.03 for a p-value, but that's still less than let's do this question. Let's just do this one. So I just did it really fast. Don't get thrown off by the parentheses. I don't know why it looks different in different problems. So it's 16 point, they want 4 decimal places. So 16.6223. We're looking at lemon imports and the crash fatality rate. I don't think those variables have anything to do with each other. Negative 0.0028. Don't forget your negative sign. Oops. By the way, here's the equation if you want to do it by hand. Anybody want to do it by hand? Oh my goodness, they want us to round the intercept to 3 decimals, but the slope to 4. Give me a break. That's so frustrating. That's ridiculous. Well, if you've made it this far in the video, I hope you enjoyed that. That's crazy. So we can use the equation. By the way, thank you for making it this far. So it'll be negative 0.0028 times, oops, 0.0028 times 475. And then I'm going to make that negative. And then we need to add 16.622. So the best predicted value to one decimal place would be 15.3. They ask, is the prediction worthwhile? I don't know if there's an outlier in this data. I don't really see an outlier. Usually an outlier needs to be way far away from all the other values. There is quite a wide range from 231 to 522, but each step seems to be about the same, so I wouldn't say that there's an outlier. The prediction is worthwhile because we did all the math. That's never the case. Just because we did math doesn't mean we get to throw out logic. Since the sample size is small, the prediction is not appropriate. I don't think I agree with that either. You can make regressions. Sometimes you only have a few data values. It doesn't make the prediction any less valuable. Since common sense suggests that there would be no relationship between the two variables, the prediction does not make sense. I would say that that's probably the answer. It's just because there's some sort of connection between lemon imports and crash rates. That doesn't necessarily mean that one variable is causing the other. So interesting. Maybe there's something worth studying in the future, but that's why that's the right answer. All right, that concludes regressions. I hope you enjoyed it. Hopefully it's not too difficult. Please let me know if you have any questions. And thank you so much for watching, and I hope you have a wonderful day. Talk to you later. Bye-bye.